Hi, this is Justin Esarey, and this week we're going to talk about decision making with statistics, or statistical decision making, sometimes related to the field of statistical decision theory. This is a field, I think, that at least in political science is not always in the main line of topics that we teach to graduate students, but it's a special topic, a special interest rather, of mine. And it's a topic that I think is really important for thinking about how we use the results of data analysis to do various things. That can include, well, we'll just set it off for a second, but there are lots of decisions one might conceivably make. And so thinking about how we make those decisions with statistics is a worthy enterprise. I want to start off with a quote from Jane's textbook on probability theory. From page 405, where he says that while we perceive a necessary distinction between inference and decision, we perceive also that inference not followed by decision is largely idle, and no natural scientist worthy of the name would undertake the labor of conducting inference unless it served some purpose. What James is reacting to here is the idea that some statisticians, some analysts, don't think statistical decision theory is important or useful for a statistician or a researcher, because research is fundamentally not about making decisions, but about finding facts, about coming to conclusions, or at most about drawing inferences about the world on the basis of that evidence, which is which should be an objective enterprise, not a decision per se. And in fact, James himself is sympathetic to this view, as you can tell by the beginning of the quote. He says later in the end of that particular chapter that it's unclear whether statistical decision theory will be an enduring part of the canon, because it's not clear that the basis of decision making that we think about today will remain the same bases of decision making for future generations. And so he goes through all these results and says, it's really interesting, but ultimately it may be the case that these things don't endure. And so our current principles of how we make decisions don't endure, and as a result, these results may end up sort of disappearing into the mists of history. I do have some ideas about that distinction, but I want to start off by just sort of boxing that particular issue off and saying maybe inference itself is a decision, and maybe it isn't. And so we can think about, for example, the idea of rejecting the null hypothesis. That's a decision we often have to make. Do I reject the null or not? We can think of that as a decision theoretic problem or not. And a little later in this lecture, I'm going to talk about what we find if we do think about it as a decision problem, and some other ways we could think about scientific inference as a decision problem that lead to somewhat different conclusions. But it's important to recognize that not every statistician believes that that's the right way to think about it. And so that some of that material is, somewhat more controversial, I guess you would say. But there are certain things that are unambiguously decisions. That is to say, no one would disagree that they are decisions. And yet they're based on uncertain evidence. So, for example, there's no doubt that the Federal Reserve makes all kinds of unambiguous decisions all the time on the basis of evidence. For example, they have to set interest rate targets. And they do that on the basis of all sorts of economic reports that they generate or consume from other agencies. So they're making an evidence-based decision. If you're going to go into foreign policy, there are all sorts of foreign policy decisions that bureaucrats and elected officials have to make that are evidence-based. Do we fund the rebels or back the government when a civil war or some other civil disturbance is underway? Do we form an alliance with a potential partner, or do we not form an alliance? These decisions have consequences which are in part based on our uncertain knowledge about the world, and there may be a way of translating our uncertain knowledge of the world into decisions. Something that's attracted a lot of attention recently is electoral design. In the United States, there's a sort of ongoing debate about how we should elect presidents. There was recently a proposal in several states to change the system from a single, well, I guess, yeah, well, they're both single member districts, from statewide winner take all to a congressional district winner take all. So each congressional district is a separate entity, and the votes for president are counted inside that congressional district and then aggregated together into the electoral college for the final presidential vote. In the presidential electoral college. This is obviously for the United States. This is sort of a subset of another class of problems in comparative politics about whether single-member districts or proportional representation systems are a better choice on the basis of a whole bunch of different potential consequences. Now, you might notice that in all of these cases, the facts of the matter are going to change what we want to do. So when growth is really high, the Federal Reserve Bank is going to make a different interest rate decision than when growth is terrible. For example, most of the world, particularly including the United States, is in slow growth at best, recession at worst case right now, state right now economically, and so interest rates are very near zero. So facts do matter. Facts are uncertain, but facts are not the only things that matter. These decisions are all a combination of facts, which are uncertain facts, and values. Which is basically a way of saying, yeah, these are statistical decisions, but they're not merely statistical decisions. We wouldn't, for example, want to delegate foreign policy decisions to an unelected statistician like me. You know, just, oh, this is just a technical problem, have Justin call all the shots. No. I may be able to help you out by figuring out what facts are going on, what the state of the world is. But I have my own values, which you may or may not share, and so values do play a role in these decisions. Statistical decisions are, in the sense that decision theory means, are a combination of both fact and value. So this is sort of why a lot of statisticians get up in arms when we say, well, statistical decision theory is an appropriate way of thinking about inference problems, because everyone's pretty comfortable with scientists, social scientists, other kinds of scientists talking about facts. But when we start to talk about values, it becomes, many scientists become uneasy. We certainly wouldn't want our results to depend in any significant way on what we value. Or at the very least, we want to minimize the contribution of our own personal value systems to the validity of our statistical results. That's the idea. Now, where this becomes tricky is it may or may not be possible to separate fact and value. There's a long literature in philosophy that debates this question, and this is not a philosophy class, so we have very limited time to consider these various arguments. But I just want to point out quickly two really quick ones. The Duhem-Quine thesis or theorem thesis. I forget exactly what it's called. The Duhem-Quine proposition, which is that no hypothesis is tested in isolation. Now, what they mean by that is that it's impossible for any researcher, no matter how well-meaning, to sit down with a bunch of data and or an experimental design and test one hypothesis. All sorts of assumptions and preconceptions go into the structure of the experiment or the design and the interpretation of the data that comes out of that experiment or research design. When we see a negative result, we may be seeing a negative result because our narrow hypothesis is wrong. But we also may be seeing a negative result because we're making faulty assumptions that to shape that analysis. This is sort of related to some later work about the Lakatosian view of research programs being sort of certain core ideas or results around which a whole bunch of ancillary results build up, and the core idea that motivates the research is never falsified. It's merely the case that the details are shifted around in order to make the body of results that that program is looking at coherent. The point of bringing this up is to say that it may not be possible to consider facts in isolation. It may be at best the case that these facts are embedded in a web of other facts from which we can't separate this one particular fact. And so the distinction between fact and value begins to break down because we are unable to unambiguously identify facts without placing them in the context of a bunch of other facts that we've decided are true. And how we've decided they're true is unclear because those facts are also embedded in another web of facts and so on. One way of saying this is we have to make assumptions, and those assumptions are going to in some way embody decisions about what we think is true and false, and we can't proceed any further without making those decisions. Some people do go further, and I'm referring here to the Pragmatist school. Now, Duhem and Quine might actually belong in this school. I'm certainly not a sufficient scholar of philosophy to be able to place them firmly in one camp or another. But the Pragmatists, the philosophical Pragmatists, generally speaking, one of their ideas is that we don't have direct access to the truth, whatever that may be. All we have access to is, James calls it, ideas that have cash value, that are useful to us. And a way of generalizing their point is that all evidence is interpreted in light of other beliefs and values. So this is sort of an extension of the idea that I was just talking about. It's impossible to look at the world and understand it without making some assumptions that ease our interpretation of the world. Let's consider the example of whether ideology affects voting behavior or other sorts of behaviors. We might find, for example, that there are all sorts of relationships between ideology and presidential vote choices, congressional vote choices. There may be even more subtle relationships between ideology and certain sorts of preferences, for example, the preference for income redistribution. If we find that these relationships are present or absent, interpreting what that means is laden with all sorts of ideas and theories and beliefs and values that we've already made before we've even begun the study. So if I construct a 7-item ideology survey instrument, and I use that to measure someone's ideology, and then I find that that survey instrument is a good predictor of vote choice in a presidential election, what have I really done? Well, what I'm going to interpret that evidence as favoring the idea that ideology, as it's been conceived by 50 or 100 years of political research, is an important influence on vote choice for all sorts of different reasons that relate to the idea of ideology as it's been formulated. What if we don't find such an example or such a relationship? For example, in some experimental work, that I did with some of my colleagues, I found that ideology is not an especially good predictor of the willingness to redistribute income in a controlled laboratory setting. Well, one interpretation is that our lab just wasn't well designed to pick up this relationship. People knew that the setting was sort of false. The stakes were too low. In other words, there might be something wrong with the test. But it might also be the case that ideology is not the right, or whatever ideology is measuring, whatever that concept is, it's not particularly associated with the willingness to provide sort of even or how do I put this? It's not well correlated with inequality aversion. Now that runs into a lot of problems with how we conceptualize ideology, because ideology in some ways, at least economic ideology, is often framed as directly being a measure of someone's desire or willingness to correct the vicissitudes of market competition, including luck, but also differential effort, by redistributing goods after the fact. There are all sorts of justifications for it. One might believe that people deserve a certain floor of income no matter what effort they put forward, for example. There are other justifications. But if you find, as we did, that there's no relationship between ideology and willingness to redistribute in a lab, the reason could be not that people don't have such a preference, or that some aspect of ideology that we think is sort of in that vein is related to that preference. It may be the case that we've misinterpreted a whole bunch of results in the past about what ideology means and how it relates to other things, because our concept of ideology was being developed and guided by a whole series of results that seemed in survey instruments and in other areas to relate to inequality aversion. In other words, when you look at our results, that ideology and redistribution preferences in a laboratory were not especially well related, you can conclude all sorts of things, and it's not entirely clear what one ought to conclude on the basis of those facts. In fact, we found in some future research that we can get some ideological effects, see some ideological effects in the laboratory if you change the laboratory setting to include risk. In other words, to include some probability of random loss, and then you find that suddenly liberals want to insulate themselves from that loss by increasing redistribution, and conservatives don't. So in other words, what we found in later research is, well, maybe it has to do with maybe it's the case that ideology is not strictly a measure of inequality aversion. It's some kind of not exactly it's not a measure of risk preference. It's a measure of assignment of assignment of responsibility for luck. Some people may assign that to the community. Some people may assign that to the individual. So that, in other words, it might be the case that ideology is a more complex concept than inequality aversion, which in retrospect shouldn't really be that surprising. Ideology, even just economic ideology, has a lot to do with a lot of factors other than how much do you like a flat income distribution. So what I'm trying to communicate here is that when you look at a positive or negative result, a sort of confirmation or disconfirmation of some hypothesis that makes sense in the light of concepts that you've already formulated, you have no choice but to interpret whatever you find in light of all the other things that you know, and in addition, in light of things you don't know. It may be the case that upon learning new things in the future, we reinterpret both positive and negative results from experiments in a completely different light. There are all sorts of physical science analogies to this. Retrograde motion of planets was, years before the development of the Copernican system, explainable by all sorts of, I forget what they're called, epicycles, I believe they were called, that posited that planets kind of just moved backwards sometimes. And you could design devices that predicted when they would move backwards relative to the Earth. And it was all sort of consistent within an Earth-centric universe. But our explanation and understanding of those facts changed quite a bit when we realized, oh, the Earth's not at the center of the solar system, the sun is at the center of the solar system. Once we knew that, all of those previous facts that we had observed changed their meaning. Retrograde motion of planets suddenly made sense, because if you put the Earth inside of a rotating system with the sun at the center, there are going to be times when planets beyond, further away from the sun than Earth, are going to appear, from our perspective, to move backwards, even though they're always moving in the same direction. So same facts, same observations, but they take on a completely different meaning in light of other things that we realize later down the road. I feel like I'm getting a bit off off the track here. The only point I'm trying to make is that there are some decisions that we know, by their very nature, involve both fact and value, these decisions that we mentioned. But it may be the case that facts themselves are not as objective or universally acceptable as we might like as scientists. And if we have to make decisions about the nature of evidence as an irreducible part of what it means to assess facts, then it's worth asking whether we might as well do that in a consistent way. So if we're going to make some kind of decision that's unambiguously a decision, such as the Federal Reserve choosing interest rates, we're going to have to find some way of integrating our preferences with uncertainty about the state of the world to produce a decision. And there are probably multiple ways of conceiving of doing that, but expected utility theory is the basis for statistical decision theory and rational choice theory in general. Expected utility theory just says that we should do whatever maximizes the expected good or utility we should receive given our uncertainty about the state of the world. So just summarizing that a bit, maximize the goodness of consequences over our uncertainty, or rather given our uncertainty. So for example, if there's some parameter that we don't know about, beta, that's uncertain, we might, and we're choosing a decision D, we might want to choose the decision, our expected utility theory says that we should choose the decision D that maximizes the utility that we expect to receive given our decision and that unknown state of the world times the probability that we think that that state of the world will happen. So expected utility theory, if you haven't encountered before, is no more complicated than the idea of figuring out a weighted average and then choosing something that makes that weighted average as big as it can possibly be. So what we've done here is to specify a couple of different bits. The first bit is a utility function, and that utility function maps decisions and states of the world into consequences. So, for example, somebody bursts into my house all of a sudden, and I decide to fight them or to run. I don't know what's happened when someone bursts into my house. They could be armed or they could not be armed, right? So if I run away, let's just say the same thing happens. I escape and the guy steals my TV. If I fight him and he's not armed, maybe I'm really proficient at fighting, so I capture him and I take him off the police and I get to keep my TV. That's good news. But there's a chance that he's got a gun or a knife, and if I attack him, then he's going to probably knife me or shoot me, and then I die, and I don't have my TV, which is a really sad state of affairs. So when I'm in the moment trying to make a decision about what to do, there's two decisions I can make. I can either fight or flight. I can fight or I can run away. And the consequences of each of those decisions depends on something I don't know, a state of the world. And so when I'm trying to figure out, well, should I fight this person or should I run for it? What I should do is I should say, well, here are all the different decisions I could make. Here are all the different states of the world that could be true. Here's my probability about each of those states of the world actually being the truth. And then I just pick the decision that gives me the highest weighted average utility. So, if I'm fighting or running, there's a chance that the person I'm fighting is either armed or not. If I fight an armed person, I get a really bad outcome, a negative 100, really bad. If I fight them if they're not armed, I get to keep my TV. That's good. If I run away, no matter whether they're armed or not, I'm a really fast runner, so I can always escape, and I get sort of the lost TV outcome. So what should I do? Well, the state of the world, which is uncertain, has nothing to do with my utility from running. I always get a negative 10. But if I fight the person, there's going to be some chance that he's armed and some chance that he's not, minus p. And so my total payoff is a function of p, the probability that the person is armed. This is all that expected utility theory says. I should calculate my weighted average return from each decision. So in fighting, that's negative 100p plus 10p, or 10-1 minus p. In the running case, it's negative 10. And then I should pick which one gives me the highest weighted average. Now, of course, I've written the original problem here as an integral. That's because many states of the world are continuous. So, for example, it may not be the person is armed or not. It may be that they have a certain fighting proficiency beta, which is continuously distributed between negative infinity and infinity, something like that. More practically, in the interest rate example, I'm trying to set interest rates according to things like inflation rates or growth rates. And inflation rates and growth rates are continuous variables. They can range from negative infinity to infinity in both cases, and anything in between. So all expected utility theory says is pick the decision that maximizes the weighted average of outcomes given all the possible things that could be true in the world. That's a very haphazard introduction to expected utility theory, but it's the best we can do in a very quick lecture. So let's talk about an example of how this works, and perhaps that will make it a little more clear. So suppose I'm the Federal Reserve, and what I want to do is I want to set interest rates for next quarter or next year, next quarter, let's say. And what I should do in order to do that is I should start with the interest rate that I actually want to be true, and then I should add on a certain inflation rate. Because if inflation rates are really high, say 5 or 6, 10%, then I need my interest rate to encapsulate all of that inflation plus my desired real rate of growth. So, for example, if inflation is 5% and I set the interest rate at 5%, what I'm really setting the real interest rate at is 0, because I lose all of my gains to inflation immediately. So this is a really simple rule that just says whatever I want the real interest rate to be, or whatever I should set the nominal interest rate at, I should pick what I want the real interest rate to be plus inflation. That's it. This is an extremely simplified Taylor rule for inflation rates. The Fed actually uses a variant of this rule, but it also adjusts for expectations. So it doesn't just pick inflation rates. It tries to figure out how much inflation is expected or unexpected by the public, by the market. This is a much simpler example, though, which will make the math easier. So what we want to do is pick an optimal interest rate given this equation. But there are a couple things we don't know. We know R star. Actually, there's really only one thing we don't know. We don't know the inflation rate next quarter. We have a guess about what it's going to be, but we don't know for sure. So we have a guess about what next quarter's inflation rate will be. Maybe this is some kind of posterior distribution on the basis of a data analysis that we've performed at the Fed. So we've got a belief distribution, but we don't know exactly what the real value is going to be. So it's got some kind of mean, and there's distribution around that mean. So this is f of pi t plus 1. And we've got to pick an interest rate target on the basis of what we expect inflation to be, but recognizing that we're uncertain about it. So what we need to do is we need to say, okay, what do we do? Well, you'll notice that if we go back to our expected utility equation here, this posterior distribution is going to map real nicely into the f of beta part of this, but we need to specify a utility function as well. So what we're going to say is that the Fed would like to hit its target being, I'm just going to drop the subscripts now, I minus r plus pi. That's its target. The further away from the target it gets, the less it likes it. So this is the gap between the ideal. This is the ideal rate. This is the rate we actually set. As that gap gets larger, we get sadder. So I'm going to put a negative out front here. And I'm also going to put a square term on because the more that we miss the target, the proportionally worse the problem gets. So here's our optimal interest rate, which is r plus pi. That's where we want to set the interest rate exactly at negative r plus pi. I'm sorry, no, r plus pi, that's right. I was right the first time. So if inflation was going to be 0, we would just set it right at r. That would be the optimal choice. But the more we miss our mark, the less happy we get. So this is the utility we get from setting I given r and pi. The more we miss the mark, the less happy we are. And even more to the point, we get less and less happy the further and further that we get from the target rate. So if I really should have, if I was omniscient, I should have set a rate at 6%, and I actually set it at 6.25. I'm sad, right? So I've set it too high. But that's far better than setting it at 6.5, or even something like 7. And the idea here is that the penalty I pay for setting it at 6.25 is going to be more than 4 times the penalty I pay for setting it at 7. So this is like Q. Here's 6.2, or say I plus a quarter. Here's I plus 1. This gap, P minus Q, or let me put it like this. Q is bigger than 4P, which is to say that getting it 4 times worse, 4 times more wrong, is more harmful than 4 times getting it a little wrong, a quarter wrong. We pay a proportionally greater penalty for getting it more and more wrong. The more wrong we are, the marginal sadness that we experience goes up. That's a way of putting it. So this is our utility function. And what we need to do is, this is also sometimes called the loss function, for the obvious reason that it measures how much we lose by making certain decisions that are off of the target decision. So what we should do, according to expected utility theory, is pick the I that maximizes the quantity negative I minus r plus pi, there's a bracket there, quantity squared f of pi d pi. So we don't know what inflation rate is going to be. We don't know that. We do have a posterior over it. I should choose the interest rate that that makes my loss as small as possible. So I'm maximizing negative loss. You could say minimizing positive loss would be the same thing. But I'm making the utility function as big as it possibly can be, given my uncertainty about pi, the inflation rate. Now, the idea is I want to pick the interest rate that no matter what happens, I'm sort of hedging my bets as best I can. I'm making the decision under uncertainty as best I can. As it turns out, this particular problem has an analytical solution. In other words, we can solve right now what this solution should be. So the first thing we need to do is just rearrange, expand terms and rearrange a bit. So if I come in here and say arg I max negative integral, I can expand out this internal function, or this square term here, to be I squared minus 2ir minus 2I pi plus r squared plus 2r pi plus pi squared f of pi d pi. Now you'll see that there's sort of a second term here that becomes its own little square term. That's because if you FOIL this top bit, you get I squared minus 2 times the quantity r plus pi quantity squared. And the r plus pi quantity squared is itself expanded. So you get this big long term. Now this is an integral over pi, so we can immediately remove and consolidate all the terms that don't involve pi. And that would include I squared, 2ir, and r squared. And then inside the integral, because we still have pi terms in there, we're left with negative 2I pi plus 2r pi plus pi squared f of pi d pi. There. Now you may wonder, f of pi was also being multiplied by this other stuff here. How come we just drop that? Well, that's because when you integrate over a probability distribution where the thing being the uncertain term is not present in the main quantity, you just are integrating a probability of 1. So in other words, consider, for example, what do we expect IR to be given that I is fixed over all the different choices of pi? Well, IR doesn't include pi in it, so no matter what happens, we expect IR to equal IR. So there it is. IR comes out. Okay, so now we can continue to consolidate a bit. We can actually break this sequence of integrals. We can break this long integral up into a sequence of integrals via basically the distributive property. So we can say I squared plus 2ir minus r squared minus, we've really got 3 integrals here. One of them is plus integral 2I pi f of pi d pi. The next one is minus integral 2r pi f of pi d pi. And the third one is, this should be a negative, quantity pi squared f of pi d pi. So we've just used the distributive property to break this up into 3 bits. Now you may notice we've got a factorable quadratic here in the front. So I'm going to change this into negative I minus r quantity squared. This here, I've got 2I integral pi f of pi. So integral pi f of pi is just the mean of pi. So what I've got here is 2I, 2I times the average value of pi, pi bar. Here I've got the same thing, except I've got 2r pi bar. And then finally I've got this last term, which looks a little bit disconcerting, pi squared f of pi d pi. But it turns out I can even collapse that down too, because this is very closely related to the second moment of pi. Pi, the inflation rate, has a variance associated with it. And if we can get the mean of pi into this expression, we can rewrite this as a variance term. In other words, what I can do is I can take this term and I can say, well, this is really the same thing as pi times whatever the deviation of pi is minus its average, f of pi deviation d pi, with the understanding that f of pi d is going to be the same as f of pi with a different mean. In other words, we're just subtracting the mean. That's all we're doing. And so if we make that realization, we can rewrite that last term in the following way. X negative I minus r squared plus 2 pi bar, quantity I minus r. So what I've done is just factored out 2 pi bar from that, put it in there. And then this last term is going to be the variance of pi. That's it. That's our solution. We need to, or that's the, now we can actually get a solution. We need to find the I that minimizes this function. Well, if you've ever taken calculus, you know that we can find the argument that maximizes this function by differentiating it with respect to I and setting that derivative equal to 0. Straightforward optimization theory. So what I'm going to do is I'm going to take the derivative of this function with respect to I and then set that equal to 0. So what happens when I do that? Well, the derivative of this first bit with respect to I is negative 2 I minus r. The second bit is 2 pi bar. And the third bit disappears because it doesn't have any i's in it. So that equal to 0. And then we can solve for I, at which we get I star equals pi bar plus r. So at the end of all that math, what we find is the ideal interest rate is just equal to the expected inflation plus r, the target interest rate. So in other words, if I expect interest to be inflation to be 5%, and I want to set interest rates at 4%, the real interest rate at 4%, I should set nominal interest rates at 9%. That's it. In other words, the uncertainty in interest rates does matter, but because we can't update it any more than just taking an average, that's our best guess. Just take the average. So this is a demonstration of how expected utility theory integrates with statistical information in the guise of an uncertain an uncertain posterior belief about some parameter of interest in the world, to produce an optimal decision on the basis of the potential consequences that might arise as a result of all the different uncertain states of the world that might appear. This is a pretty easy problem to solve. It has an analytical solution even. But in general, statistical decision theory problems that involve uncertainty are not going to have analytical solutions quite as easy as this one. First of all, we're unlikely to have a posterior distribution over a parameter like pi that's quite so easily tractable. In other words, it's not going to be a unidimensional distribution like this one is. Probably we're going to have multiple parameters that we're uncertain about, And each of those parameters is going to enter into the utility function in a different, complicated way. Once that happens, analytical solutions might be a bit hard to find. So in general, if we're trying to make decisions with statistical information, uncertain information that comes out of statistical analysis, we're going to have to find optimal solutions by doing this kind of procedure numerically instead of analytically. So let me show you an example of how you could do that for this problem, and in this case we'll have the benefit of seeing that the numerical solution is the same as the analytical one. Alright, so let's do this same decision theory problem that we just did analytically, but try tackling it computationally instead. And like I said earlier, most problems in decision theory, applied problems rather, will be complicated enough that there probably won't be an analytic solution, so you have to do it numerically. So what I'm going to do is start off by plotting a bunch of interest rates from -1 to 7. I'm sorry, not interest rates rather, but inflation rates from -1 to 7, just to show what I'm going to assume about the posterior density of interest, or of inflation rather. So, in fact, maybe I'll just add in a label. So, posterior beliefs about inflation rates. Oh, that should be a comma. There you go. So what I'm going to assume, in other words, is that this is the result of some kind of analysis that's telling us what we expect inflation to be in the next quarter. We expect it to be centered on 4%, but it could be 6, it could be 2. There's even a small possibility it could be negative. We could have had deflation, but it's a very small chance. So what I'm going to do is use this data and come up with a decision about which interest rate I should set given that posterior belief, if my utility function is this right here. So this is the same function we wrote down. It's I minus r quantity r plus p squared, negative of that. So that's the utility function bit. And then the d norm here is just our this posterior belief right here that we've integrated into the utility function, into the loss function. Now, I have to compute an integral of this loss function over all of the different values of the inflation rate that could be true, because I need to minimize my loss or maximize my utility given my distribution of beliefs about probable inflation. So what I'm going to do is first do this sort of simply using graphical plotting. So I'm just going to propose a bunch of different interest rates from 0%, which is usually the minimum. You can't, technically speaking, it might be possible to set negative interest rates, but 0 is more or less as low as it goes when it comes to the Fed. Up to 10%, which is not as high as it could go, but it's a reasonable upper maximum if we're looking at this kind of posterior belief about inflation. So what I'm going to do is propose all these different interest rates and plot the loss integral for each one of them. So I'm going to calculate, in other words, expected utility for each one of these values of the interest rate, and then I'm going to figure out which interest rate has the maximum interest rate the maximum utility by plotting all of my different proposals against utility. So this is the loss or utility. This is the interest rate. So what I've done is I've gone up here and I've made loss as in some senses as big as possible. They're all negative numbers, so you can think of like we're keeping losses as small as we can get them, but it is also in a sense maximizing it's maximizing utility because the loss function gets more negative as you move away from the optimum point. The optimum point, as you can see, is going to be somewhere around 8. Does that make sense given our previous solution? Well, we've said that R, the target interest rate, is 4. There's R right there. We've targeted 4%. And our distribution of beliefs about inflation is also centered on 4. So what we should do is, according to the analytic solution, say, well, the ideal interest rate is the average inflation rate, or 4%, plus the target of 4%, so 8%. So yeah, it seems to be matching that solution well. Now, as I mentioned, you probably aren't going to be able to do most of these problems analytically. You're probably also not going to be able to do them via simple graphing like this. This works fine if the loss function is reasonably easy to write down, and more importantly, if you've only got one parameter that you're maximizing over a fairly short interval. More generally, we're probably going to want to use some kind of numerical optimization technique to find the ideal interest rate. And what you can see here is I've just used the optimize function, which is designed for one-dimensional optimization. If you had multi-dimensional optimization, you could use optim instead. And I've told optimize that I want to compute the maximum, so you can see I'm saying maximum is true because we're actually maximizing utility here, of the loss integral function. So we're maximizing the integral of expected utility, or expected loss. And I want to try choices for I, the interest rate, between 0 and 10. And I also have to specify that the target rate is 4. So R, the target interest rate, is 4. And very quickly, the optimize command comes up with the answer of precisely 8, which again makes sense given our analytical solution. So if we had a more complicated problem that had more parameters to choose, or a much more complicated loss space, we could use numerical optimization like this to compute the utility maximizing answer, even if it wasn't so easy to visualize or analytically solve. So as I mentioned earlier, it is possible to conceive of the inference problem itself as a decision theoretic problem. For example, we could propose the following question: what is the best estimator of an unknown quantity or effect beta? Now, we have to assume that we know a little something about the form of the problem, and I'll talk a bit what I mean by that in a second. It has to be a well-specified problem where even if we don't actually know what beta is, we can say some things about it that enable us to do certain things. For example, we have to know enough about the problem in order to be able to write down something like this. Well, a loss function for my estimate of beta, if I call my estimate of beta hat, a function of x, or observable data, minus beta, the true value, squared, that's going to be my loss function. I'm going to put a negative in front of that to indicate that we're going to try to minimize maximize the negative of that loss. We could also just leave it positive and talk about minimizing that loss, but whatever. Anyway, what we're going to do is we have to know, what I meant earlier is we have to know enough about the problem in order to think about there being a parameter beta that we can in principle estimate in some fashion using beta hat, our estimator, and a bunch of data x. It turns out that if you think of inference as this kind of problem, trying to write down an estimator of a quantity beta hat that minimizes this kind of squared loss, you get a really interesting conclusion about what an optimal estimator looks like. So what I want to do is set up a problem of trying to pick the best estimator of beta as an expected loss problem, where I'm trying to, we'll say I'm trying to I could either maximize the negative loss or minimize the positive loss. We'll say I'm trying to minimize the positive loss. Double integral of beta hat x minus beta quantity squared, that's my loss, times f of x given beta, because we have to integrate over all the possible data sets we could encounter in the world given all the different possible values, or fixing all the different possible values of the true parameter beta, times f of beta d beta dx. So in other words, what we're saying here is we're going to integrate out beta integrate over all the different possible values of the true parameter or true estimated quantity, whatever that may be, beta. We're also going to integrate out all the different possible data sets we could encounter, x. And over those two continuous quantities, we want to get the estimator that gives us the smallest expected loss possible. Saying that a little more straightforwardly, no matter what data we expect to encounter, given our knowledge of the distribution of the data in the world, and no matter what quantity we encounter, given our knowledge of the distribution of the quantities in the world, we want to figure out an estimator that will minimize our expected loss over both of those sources of uncertainty. Now, that's the problem. So I'm going to step aside for a second, because solving this problem is going to enable us, or is going to require us, to do some somewhat complicated things with calculus. So if this were a really simple function like g of beta and x, and we wanted to find the beta star that minimized or maximized g, so if we want to find the beta star that minimized g, what we could do is we could take the derivative of g with respect to beta and set that equal to 0, and then solve for beta. And as long as actually I should say, really this is three things: beta hat, beta, and x, and we want to find the beta hat star that minimizes g. So dg beta hat dg d beta hat is 0, and solve for beta hat, because we're solving for an estimator. Anyway, if we wanted to figure that out, all we do is set the derivative equal to 0 and solve for beta, and as long as the second derivative conditions were met, which is to say as long as we were at a minimum and not a maximum, we'd be done. The issue that we have in this problem up here is that the optimal estimator, beta hat, is not a quantity, it's not a variable. It's actually a function. And E, the expected value of L, the expected loss, is a function of that function. So we can actually go through a similar process with calculus, but it's a little more complicated, because we're not taking derivatives with respect to a parameter, we're taking derivatives with respect to a function. So what we're doing is we're taking the derivative of the expected loss with respect to the function beta hat, which follows similar rules as variable derivatives. For example, the exponent rule that follows from derivatives still works. We can take the derivative here and get 2 times the quantity beta hat function of x minus beta times f of beta times f of x given beta d beta dx. You see I reversed the order of these two things. That's just to keep, actually, in fact, I probably should write it that way up here too. We'll do this, f of beta, f of x given beta, to recognize that we're integrating out beta first. That's the order of integration in this case. If we were doing, this is, incidentally, I should note, is an idea from what's called the calculus of variations. I am not a world-renowned expert on variational calculus, but I do know enough about it to know that there are analogs between this sort of calculus and basic functional calculus that hold for this problem, such as the exponent rule works for this problem in a way similar to that would work for standard sort of functional calculus, a variable style calculus. The only problem we have in this calculus of variation type problem is that if we want to do our normal thing and set this equal to 0 and solve, you might notice that the value of this quantity actually depends on x through f of x given beta. and then through the fact that beta hat is itself a function of x. Now that second bit is not so important because we're changing the function of x, not the we're changing the function beta hat, not its particular value for x. But the fact that we're integrating over x sort of brings that dependency back in, because the shape of the data space, the distribution of the data, being different could change what sort of estimator would be optimal. In other words, there is still dependence on the data space that we'd really prefer not to have in order to make this work. So I can't just set equal to 0 and solve for beta, because I've got this x in here that's relevant. And more to the point, I wouldn't want my optimal estimator to depend on x. I want it to be the best option no matter what x I might encounter, given my knowledge of the distribution of data in the world. Now it turns out that what I can do to get myself out of this problem is to say, well, this whole expression will be equal to 0 as long as this internal expression right here is equal to 0. So if that integral equals 0, then the outer integral is just the integral of zeros, which itself integrates to 0. So in other words, there are lots of ways I can add a bunch of things up to get 0. One of them is for all of the things I'm adding up to themselves equal 0. That's kind of a way of putting it. So what I can do is I can say, well, this is going to be true if this is true. Beta hat x minus beta times f of x given beta d beta equals 0. So, I'm sorry, I need to put an f of beta in there too. My mistake. F of beta d beta equals 0. There we go. So as long as the inside integral is 0, the outside integral is also going to be 0. So maybe we can find an expression for which this works. And I should say, the reason this is especially attractive is it means that we don't have to, it doesn't really matter what the data set looks like, because it's true for any value of x. If this expression right here, if this is true, then it means that our answer is in some sense independent of the distribution of the data, which is an attractive quality. It's a good feature. Okay. Now I can solve this for 0. How am I going to do that? I'm going to break the integral up into 2 bits by distributing this parentheses here, and then breaking the integral into its sum. So in other words, I can rewrite this as the following: beta hat x f of x given beta f of beta d beta minus integral beta f of x given beta f of beta d beta equals 0. That works. You can break up a sum inside an integral into the integral. The integral of a sum is equal to the sum of the integrals. So that's a perfectly acceptable thing to do. Now what we need to do is rearrange terms and factor out the things that don't belong in the integral. So I can move this left-hand side over here and say the integral of beta times f of x given beta, f of beta d. Man, my writing is terrible. Let me try this again. Try to be at least somewhat careful here. The integral of beta, f of x given beta, f of beta d beta equals the integral of beta hat x f of x given beta f of beta d beta. Now I'm integrating over beta here, so I can factor out this multiplicative quantity and rewrite that as beta hat x integral f of x given beta f of beta d beta. And the fact that I've integrated out beta of f of x given beta means that what I'm left with on this side is beta hat x f of x. I've integrated out beta. On the right hand side, I still have integral beta f of x given beta f of beta d beta. So if I want to solve for the estimator beta hat x, I bring over f of x, and what I get is integral beta f of x given beta, f of beta d beta divided by f of x. That is the optimal estimator. And this is going to look very familiar. It may already sort of look familiar. If I rewrite this as the equivalent expression, integral, hold on a second, integral f of x given beta, f of beta d beta divided by f of x times beta. Just a second, I want the, there we go, I want that. I want the d beta out here. You can see this right here, this bit, is the posterior for beta given data. In other words, this is f of beta given x per Bayes' rule. That means that this whole expression, get another color here, this whole expression is the weighted, posterior weighted mean of beta. So in other words, the best estimator of beta is the average beta given by weighting via the posterior. Another way of saying this, even more simply, if I want to know the best estimator of beta hat, or I'm sorry, if I want to know the best estimator beta hat, and I've got a posterior distribution, so here's beta, here's f of beta, my optimal beta hat is the mean of this distribution. Beta hat star is the mean of that distribution. The end. That's really interesting because what that implies at a sort of deep level is that Bayes' rule is intimately linked with the optimal way of computing, of estimating a quantity. Nowhere in this proof did we ever say anything about posteriors or Bayes' rule or anything like that. It just appeared. It appeared because Bayes' rule is, as we've seen, the best way of minimizing the expected squared loss. Go back to the loss function. The expected squared loss between our estimate and the true value. Now, it turns out that you can get somewhat different answers if you assume a different loss function. So we assume squared loss. If you assume absolute value loss or square root loss or other things, you can get other answers. In fact, in the Bishop book, they talk about different loss functions relating to different answers. I believe one loss function can give you the mode of the posterior as being the optimal guess. Another of them can give you the median. Now, in this little sample here, they'd all be the same because the mode is the median is the mean in a symmetric posterior like that. But if you had sort of an exotic looking one where you had a big hump over here and like a long tail, something like that, which is, you know, perfectly possible, you might have a mode here and a mean, you know, somewhere out here and a median somewhere out here, and different loss functions would tell you that different of these quantities is the optimal estimator. That's fine. I believe all of them ultimately end up producing a version of Bayes' rule. It's just a matter of what function of the posterior you're going to end up taking. Anyway, that I think is a really interesting result that's worth contemplating. This is a way in which statistical decision theory or optimal decision making actually links back to inference. We are in some ways making optimal inferences when we show the mean or the mode or the median of a posterior using Bayesian inference per Bayes' rule. And of course, frequent to statistics links back as well, because if our prior is flat, then the Bayesian answer, the Bayesian mean, Bayesian mode, is posterior mode, is going to be equivalent to the frequentist maximum likelihood result. I should say, to be clear, I believe it's the if it's flat and the posterior is symmetric as a result of that flatness, which it almost always will be, although I could think of some cases where it wouldn't be, maybe. The frequentist maximum likelihood estimate would always be equivalent to really any conceivable estimate that you get out of a posterior. In some more exotic, more generally speaking, the maximum likelihood estimate will be equivalent to the posterior mean. I think it's the posterior mean. So maximum likelihood and frequentist results are also sort of implied by this, as long as you're willing to accept a flat prior. So that's a really interesting link between decision theory and inference, and it tempts us, or at least it tempts me, to go forward and start to ask more questions about how statistical decision making or optimal decision making might relate to other inference procedures that we use. So in principle, it's possible to make a lot of decisions via formalized statistical decision theory. We could think about making all kinds of complicated decisions about the relationship between a theory and evidence on the basis of some loss function that we've specified. But this could get really complicated, and it would be very hard to ensure that the decision problem was formulated in such a way that would be acceptable to all the different scientists and researchers who would be looking at this evidence. So the usual thing to do, and this is why earlier I mentioned that lots of statisticians really prefer to think about inferences as not being decision-based, is to just present the evidence and let the chips fall where they may. Have readers read what you found and make their own decisions. But nevertheless, we still are making lots of decisions. One of them is, should I reject the null hypothesis or fail to reject the null hypothesis? It's a decision that every frequentist statistician makes hundreds of times a day. And you might say to yourself, well, maybe not hundreds of times a day unless you're doing hundreds of regressions, but whatever. Anyway, you at least are thinking about that when you're reading some kind of some paper. And it's true, you don't necessarily have to make the decision and just report that decision and never report the evidence. You could report p-values and let readers make their own decisions about what's going on. But everybody knows that the 5% threshold for a p-value or a t-test is a very common thing that's going to get used as a metric of acceptability or interestingness, or at least a minimum threshold, a minimum requirement to be taken seriously as evidence. By every reader, by every journal editor, that's a very common thing that's going to happen. So even though in principle we don't have to make these decisions as researchers, we can simply report p-values and let the chips fall where they may. We all know that when we read these pieces and decide whether to include them in journals, decide whether to take note of them, assign them in classes, and all these things, one of the things we're asking ourselves is, in my head, implicitly, should I reject the null or not? And if I should, that means not that I believe this evidence or believe that the theory is true or whatever, but at least I'm going to start thinking more about what this evidence means. If I can't reject the null hypothesis, for many people, the decision the thought process ends there. This evidence can't be distinguished from chance. Game over. So even though a researcher maybe doesn't need to force this decision into a paper, nevertheless, and when other people read it, when journal editors read it, they're going to be making these decisions, and so the decision comes back. It's always there. I mean, any researcher is going to encounter this sort of decision when people are reacting to his or her work. And although it's not usually stated this way, it's actually possible to justify the null hypothesis testing procedure on a decision theoretic basis. Let me show you how this might be done. So what I'm going to do is I'm going to consider two different decisions. I'm going to consider the decision to reject the null and the decision to fail to reject the null hypothesis in any given work. And so what I'm going to say is that there's some utility associated with both of these decisions. The utility is basically just what do researchers expect to get out of considering this evidence versus ignoring this evidence on a scientific basis. Now, I'm actually, what utility we get out of ignoring versus not ignoring evidence is rather controversial. But the null hypothesis testing procedure with 5% thresholds and all that actually implies a certain utility function, like so. So the expected utility of this decision is going to be a function of a couple of things. I'm going to specify the alternative hypothesis that beta is greater than 0, which implies that the null hypothesis is that beta is less than or equal to 0. So this is just a one-sided testing sort of framework. So that means that if beta really is bigger than 0, then we assume that this difference, reject versus you fail, is probably positive. It's the right decision to make to reject the null. And if beta is less than or equal to 0, it's the wrong decision. And actually, I should have made this conditional here. I apologize. So I need to, let me erase this real quick. So you reject given beta is greater than 0 minus you reject given, I need to erase all that. You fail given beta is greater than 0. Anyways, I was saying we expect this quantity to be positive in cases where we're right, where the null ought to be rejected. And then there's, of course, a chance that beta is not equal or not bigger than 0, in which case you reject given beta less than or equal to 0 minus you fail to reject given beta less than or equal to 0. We expect this quantity to be negative. So in other words, when we reject a null hypothesis when we ought not to, we expect that to hurt. So what I'm going to do is I'm going to replace these two big quantities with just fixed numbers. I'm going to say, well, there's a chance that we reject the null and we're right. And if that happens, we get alpha. And there's a chance that we reject the null and we're wrong, and if we do that, we get gamma. Two parameters. I can rewrite the probability that beta is greater than 0 and the probability that beta is less than 0 in terms of posterior probability densities. So, in other words, the probability that beta is less than or equal to 0 is simply, here's the posterior of beta, here's beta, here's f of beta, and we got to specify a 0 here, there's a 0, just the integral of that probability density to the left of 0. And the probability that beta is greater than 0 is just the area of the integral to the right of 0. These are both given by the cumulative density of little f of beta, or in other words, cap f of beta. This requires a bit of finessing if we're going to apply this to the frequentist framework, because of course the frequentist distribution of a parameter, beta, so the estimated variance covariance matrix of beta hat or whatever, is not technically the posterior of beta. It's the sampling distribution of beta. It's an estimate of the sampling variance of beta, right? Nevertheless, the frequentist solution to this problem is identical to the Bayesian solution with flat priors, and so we can say that with a relatively minor, essentially philosophical reinterpretation of the evidence, this is equivalent to the frequentist inference procedure. In other words, we are acting as though we are considering these as posteriors under a flat prior. Just making a note that there is a bit of a technical issue there. Okay, so if we're willing to assume that frequentist answers are Bayesian answers under a flat prior, and we're willing to thus accept that these posterior densities are the same as the estimated, are determined by the estimated variances in a frequentist analysis, then what we can do is say, well, what we want to do is make the decision. I'm sorry, that should be a gamma. We want to make the decision to reject whenever this quantity is bigger than 0. That's when we want to reject, whenever the expected utility of rejecting is bigger than 0. And so if we rearrange terms and solve, what we get is the following. Okay, so I've got to distribute alpha. I've got to bring f of 0, get f of 0 on its own. So I'll bring this over to the other side. And this is going to be gamma minus alpha is greater than alpha. And then we've got to divide, so we get f of 0 is greater than alpha over alpha. Or if we put a negative, if we sort of flip the sign, we can alpha over alpha minus sigma. Oh, no, I actually made several mistakes here. First of all, this should be bigger than 0. The estimated or the expected utility of making the decision should be positive, in other words. So I need to flip these signs. For some reason we screwed this up. And I also reversed these coefficients here, so this should be alpha minus sigma. Yeah. There we go. So that's where we want it to be. Alpha minus sigma. And right. Is that right? No. Wait. Right, so this should be here, and that should be there. So the probability that beta is less than 0, in other words, we could rewrite this as the probability beta is less than 0, that's the equivalent to that, should be less than some quantity, alpha divided by alpha minus sigma, where alpha and alpha minus sigma give the utilities, respectively, to correctly and incorrectly rejecting the null. Now, the usual rule, the 5% rule in hypothesis testing, is that you only reject when f of 0 is less than 0.05, which implies this. So then we can solve for the relative relationship between these two quantities. We can say that 0.05 alpha minus 0.05 gamma is less than alpha. Let's see. Yeah, so we add, okay, we can subtract alpha from both sides and get 0.95 alpha is less than negative 0.05 gamma. Then we can divide by, I'm trying to think which one I'd prefer to solve for. This is going to be the benefit to correct rejection. This is going to be the disbenefit to incorrect rejection. So actually what I might want to do is solve in terms of the ratio. So probably what I want to do is divide both sides by 0.95, so negative 0.05 divided by 0.95, and then divide both sides by gamma. So I get here alpha over gamma. So the ratio between harm to benefit, actually, really, maybe it might be best to do it this way. 0.95 divided by 0.05. Oh. 0.05 is greater than gamma over alpha. So the disbenefit to incorrect rejection has to fulfill a certain ratio of harm compared to the benefit of correct rejection. And we can take a quick detour into R and figure out what that ratio works out to. 0.9, oops, 0.95 divided by 0.05 gives us 19. Go back to my notebook here. So negative 19 alpha is less than gamma. So in other words, what this is saying is this decision procedure makes sense if the harm that I suffer from a false positive is 19 times worse in the opposite direction as the benefit of a correct rejection. Yes, of a correct rejection of the null. In other words, the statistical hypothesis testing procedure that we're all used to, rejecting the null whenever the t ratio is less than 1.96 in a two-tailed test, or really this is a one-tailed test, so it's really more like 1.645. That's a good thing to do. It makes sense from a statistical decision theory perspective if two things are true. First, we have a 1-0 loss function where it doesn't matter how much I miss a predict, or I'm sorry, how badly I get it wrong. All that matters is whether I get it wrong or not. So I get benefits from correctly rejecting the null, and I get harm from incorrectly rejecting the null. That's the first assumption. The second assumption is the disbenefit I get from incorrectly rejecting the null has to be 19 times worse than the 19 times larger and in the opposite direction as the benefits I get from correctly rejecting the null. So if those two things are true, then the null hypothesis test statistic procedure that we all use is justifiable via statistical decision theory. That's kind of interesting. What it says is, this makes sense if you really care about signs and not about size, effect size. Effect size never comes into it. All that matters is, do we get the sign right? And you really, really hate incorrectly rejecting the null. It's nearly 20 times worse to incorrectly reject the null than it is to correctly reject it. So if those two things make sense together, then and you're happy with that, then you should be really happy with the null hypothesis test statistic. Or I'm sorry, the null hypothesis test procedure, because it is coincident with those with rational decision making under those preferences. So the 1-0 loss function, or step loss function, that justifies the statistical significance test procedure from a decision theoretic perspective, that loss function is far from universally acceptable. And let me show you a quick example of why you wouldn't always have that sort of loss, or have that sort of loss function. So imagine I give you two evidence-based decisions that rely on the same shape of evidence, the same basic underlying problem. On the left-hand side here, what I've got is a problem where there's a weight loss drug. It's very effective. You can lose as much weight as you want just by taking a pill. It's a wonder drug. If anybody discovered this, they'd be really rich. Problem, it might cause cancer. So we do a study and we try to figure out what's our posterior belief that this drug causes cancer. What's the proportion change of cancer risk after you take this drug? Assume there are no problems with the experiment. It's a perfect experiment, no control issues or anything. This is our posterior belief, okay? So the proportion change in cancer risk, most of the density of the posterior is concentrated to the right of 0. The average is actually a 25% increase in cancer risk. But the effect is not statistically significant. As you can see, there's a greater than 5% area shaded over here. In fact, I believe it's a 25% area shaded to the left of the curve here. So there's a 25% chance that the true relationship, assuming there is a true relationship, there's 25% chance that it's either 0 or even less. Maybe the drug not only doesn't cause cancer, it makes you less susceptible. So if you look at this posterior, would you take this drug? You might say yes, you might say no. Probably your decision won't be based on the fact that this effect is statistically insignificant, though. I think most people would look at this and say, I'm not taking this drug. There's an excellent chance that it was going to increase my cancer risk, and I would expect it to increase my risk by 25%. So the fact that you're making a different decision that would be implied by statistical hypothesis testing tells you that utility function is not always the one I'd want to use. That loss function is not always the one I'd want to use. But then again, if I take this exact same posterior and I just change the question, then you might well use this procedure. So I might tell you, hey, would you believe that non-democracies have more civil wars than democracies? And I do a study. Again, suppose the study is perfect, the data is perfect, and I come up with a posterior belief density of the proportion difference in intrastate conflict risk between non-democracies and democracies. And it's shifted to the right, so there's a positive relationship here, but a lot of the posterior density is actually to the left of 0. So there's a 25% chance that the relationship between democracy and war risk or civil war risk is positive. It actually causes civil wars. So would you believe, if I showed you this evidence, that autocracies are more susceptible to civil war? Many people would say, no, I wouldn't believe that. The effect is not statistically significant. You know, it's not even close. And so there's a pretty good chance that, you know, that democracy has nothing to do with it at all, or maybe it's even a risk factor for interstate conflict. And so, no, I'm not going to believe this. So what we have to do is figure out what is it that is different about these two problems that leads us to make two different decisions. And maybe come up with a way of recognizing that different researchers can even apply different standards to the same problem, might come up with different decisions, and that leads us to start to think, well, how might we come up with a way of figuring out how robust certain inferences or conclusions are to different standards of evidence? So the idea here is that we might be able to figure out a function that's better able to represent diversity in preferences that people apply to the interpretation of evidence. And so let's consider a bunch of different, actually not really a bunch, just a few different utility functions we could conceivably use. And what I'm going to do is I'm going to say that the alternative hypothesis here we're considering is whether to reject the null that beta is less than or equal to 0 in favor of the idea that beta is bigger than 0. So 0 is the cutoff. Now, the null hypothesis testing framework implied by statistical significance testing says, well, your utility for being wrong is given by gamma. Your utility for being right is given by alpha. It's the same no matter what beta is. And make your decision accordingly. We've already found that utility function is consistent with the accept, reject statistical significance testing framework. But there are other ways we could look at the problem. For example, we could look at the problem this way. We could say, well, it's really kind of weird that an error that's just a little bit to the left or a little bit to the right of 0 is counted the same as making a giant error. Those are weighted the same in the null hypothesis testing framework. So maybe what we should do is say, if beta is equal to 0, it doesn't really matter what we decide. You can reject or accept, the consequences are going to be virtually nil. If beta is actually slightly positive, then accepting it is good, but rejecting it is not all that bad. It's not that important. And the importance of rejecting beta gets larger, or rejecting the null, rather, I'm sorry, get larger as beta gets larger. But as beta gets smaller, the consequences are less than, the beta gets more negative, I guess I should say. The consequences of rejecting this null in favor of this alternative get worse. And those consequences are get worse faster than the consequences of correctly rejecting the null get more positive. So in other words, making the wrong decision gets worse and worse and worse. Rejecting the null falsely gets worse and worse and worse as we as beta becomes more and more negative, much faster than the good consequences of correctly rejecting beta get more positive as beta gets larger. So it's on the x-axis here, I'm sorry, apologize, what's on the y-axis here is the net utility of acceptance. I'm sorry, reject. Given beta. So in both of these cases, the difference is given beta. So given beta minus you accept given beta. So the it's obviously what this red function tells you is rejecting beta when beta is positive is good. The bigger beta is, the better it is to reject the null. But if beta is actually negative, it's bad to reject the null. And the more negative beta is, the worse it is to reject the null. And it's proportionally worse than mistakenly accepting the null when beta is positive. These are not the only two options. There are many others. Let me just show you one other possibility. A so-called risk-averse function might look a little something like this. Man, that's a terrible curve. Let's see if I can do better. Geez. Hold on. I need to arrange my pad a little bit better. Oh, I just turned it off. That's great. There we go. So this is the same sort of idea. This is a very poor drawing approximation of a CARA, constant absolute risk aversion function. What it says is that it's sort of the same idea as the red function I just drew, except that instead of things being proportionally the same, so in other words, an increase in beta size always causes a proportional increase in the utility from correctly rejecting the null. An increase of a certain size where we reject beta falsely, where beta is really negative, causes a proportional decline in utility. The constant absolute risk aversion function actually presupposes increasing utility of incorrect rejections and decreasing marginal utility of correct rejections. So it's a related idea. It just puts even more weight on avoiding nulls. I'm sorry, on avoiding false positives. Avoiding false positives. So what I propose to do here is to not to impose any of these utility functions on somebody, but rather to say, well, let's choose one of these, and what we're going to do is figure out some ranges of flexibility. I'm sorry. So figure out some ranges of disagreement about the interpretation of evidence that would cause people to make a different decision. And so the one I'm going to focus in on is this red line, which is actually what we call in the paper that's associated with the idea with Nathan Damon, we call this a loss aversion function. The idea is that a person with this utility function is averse to losses, which is to say they don't like making wrong decisions, but they proportionally don't like making they like false negatives more than they like false positives. And so what we do in the paper is we allow there to be two dimensions of disagreement among researchers on the standards that they choose to apply to evidence. One of those ranges of disagreement is how loss averse they are. So let me see if I can do a decent job of depicting this. A person who's perfectly neutral to losses would have a function that looked like this. That is to say, they would value false positives and false negatives equally. If they liked false positives less than they liked false negatives, we would have a kink in this direction where the utility from a false, so again, we're assuming the null is beta is greater than 0, and we're deciding whether to reject that null or not. So this is centered right here. They like false positives more than they like false negatives. That's the downward kink function. It's actually possible to even have an upward kink function, something like this, which is the idea that people like they wish to avoid false negatives even more than they wish to avoid false positives. And that may sound implausible in a statistical sense, but we'll see in a second there are actually many decisions where a false negative is far worse than a false positive. We functionalize this idea by writing down a relatively simple mathematical expression which corresponds to this graphical framework. The utility of acceptance given beta minus the utility of rejection of the null given beta. I'm sorry, I've written this wrong. Utility of rejection given the utility of failing to reject or accepting the null equals a gamma to the power of the negative sign of the expression beta minus c times the quantity beta minus c. That's what this looks like. These functions all correspond to different values of gamma, gamma 1, gamma 2, gamma 3, when c is 0. And c is actually going to be the intercept of this function. The x-intercept, I should say, of this function. Now, it turns out that, you can see just by looking at this, that by changing c, we allow there to be another dimension of disagreement or a different range of evidentiary standards that researchers could choose to apply to evidence. For example, if we specify a bigger c, we take this blue function here, for example, with gamma equal to gamma 3, and if we move c up, we move it over, just like so. So this corresponds to increasing c. Increasing c. What increasing c corresponds to is not the relationship between false positives and false negatives, but rather what counts as a false positive or a false negative. What counts as a positive or a negative, really. If we move c to the right, as I've done here, so that c is equal to some quantity bigger than 0, what we're saying is, instead of merely accepting whether beta is bigger than 0, we're going to look at whether beta is bigger than c, bigger than some quantity. And this makes sense because there are lots of possible relationships that may exist, but are far too small to be substantively meaningful. I mean, if I find that some drug has a 0.00001% decreased risk of cancer, right? And somehow I do a study that has infinitely small variance, so I can actually get a statistical significance on that effect. I probably am not going to get approval from the FDA to sell this drug as an anti-cancer drug, even if I'm certain that that's its effect, because it's just too small to matter. I mean, nobody cares about something that small. So, and the same goes for political science. Nobody cares about an effect that small on civil war or electoral success or anything. You can't even sell that. You can't sell it to anyone, even scientifically. So there may be different standards for what counts as the minimum size that is really worthy of attention by a researcher. So what we're going to do is we're going to start with that utility function, and we're not going to say that the utility function is the true one or anything like that. We're just going to say, well, these two dimensions of change, gamma and c, represent two dimensions of disagreement among researchers about how to interpret evidence. The false positive, false negative trade-off, and the minimum effect size that would make sense to accept. And what we're going to do is we're going to produce a plot like this that corresponds to whether a decision would be acceptable or not for a given level of loss aversion, that's gamma here on the x-axis, and a minimum size threshold c. So the line is the line that divides acceptable decisions from non-acceptable decisions. Now, what do I mean by that? Well, let's say that my level of loss aversion is, and I'm just totally picking this out of the air, it's 2. Okay, there's my level of loss aversion. Okay, oops. Man, I'm terrible at drawing. Now, if I believed that an effect of, say, 2.5% increase in civil war was meaningful, I would be willing to reject the null. I would be willing to say, yeah, C's, the relationship between democracy or between autocracy and civil war is at least 2.5%. I'm willing to say that I'm willing to assert that based on this evidence, autocracies are at least 2.5% more likely to experience a civil war. I'm not willing to say on the basis of this evidence that they're 15% more likely. It's just not strong enough. Not strong enough evidence to convince me of that. A person with a lower level of loss aversion, however, would be willing to say that. So a person with, say, this is here, this would be like, gamma, this is gamma 2. Now I'm down to gamma 1.25. I would be willing to say that. I'd be willing to say, yeah, it causes a 15% decline on the basis of this evidence. I would say that. But I wouldn't be willing to say that it causes a 25% relationship. All I'm doing is I'm solving this function. I'm seeing whether this function is bigger than 0 or less than 0. I'm willing to say, would I reject the null that the effect is less than 15% or not? And a person with a really low level of loss aversion would reject that null, but a more loss averse person would not reject that null. In other words, if I'm more tolerant of false positives, I'm more willing to assert stronger conclusions, larger effect sizes. The point of producing these graphs is to show, okay, what sort of conclusions about effect size would a person be willing to accept? In other words, would a person be willing to reject the null of at different levels of loss aversion? And what I've done here is I've plotted these two graphs for the two different examples, one involving cancer risk and one involving war risk that I introduced earlier. The key difference between these two problems, the take a weight loss drug that might cause cancer or accept that autocracies are more likely to go to civil war. In my opinion, the main difference between those two problems is that in the cancer problem, being wrong about the drug causing cancer, which is to say a false positive, not that important. If I accidentally don't take the drug because I'm afraid it causes cancer, but actually it doesn't cause cancer, that's no big deal. If I think the drug doesn't cause cancer, and it actually does, which would be a false negative, I'm screwed. I've just taken a drug that's going to cause cancer. The opposite is true in the case of democracy and war risk. In that case, a false positive accidentally saying that that democracy, or in this case autocracy, causes civil war, accidentally saying that is really harmful. Accidentally saying a drug causes cancer, not harmful. Accidentally saying that civil war is caused by autocracy, harmful. So the difference, in short, is the gammas that make sense. A gamma less than 1 makes sense in a problem where I'm mostly concerned about false negatives, such as this problem. And a gamma bigger than 1 makes sense in this problem where I'm mostly concerned about false positives. And if you look at these graphs, on the left-hand side in the cancer risk problem, what you see is that I'd be willing to assert that there's at least a 30% chance, maybe even more, that the drug causes cancer for virtually any level of loss aversion less than between 0 and 1. 0 being the theoretical minimum. 0, incidentally, back on this graph, would correspond to a loss aversion that was like this, almost like an L shape. So, of course, I'm not going to take this drug because no matter what my preferences are, no matter how much I may weigh the consequences of false negatives against false positives, I'm willing to accept that there's a large effect between this drug and cancer. In the democracy problem on the left-hand side here, I don't have to be very averse to false positives before I will conclude, here's a 0 right here, that there's no effect at all. In other words, the conclusion that autocracy is associated with civil war risk is reasonably sensitive to disagreements about loss aversion, such that, that going from a 1.5 to a 2 to a 2.5 really drastically decreases my willingness to assert that there is an effect, my willingness to reject the null hypothesis, if you want to put it that way. And to give you some sense about what these gamma coefficients actually correspond to so that we can relate them to real quantities, gamma squared is the proportion that false positives are weighted compared to false negatives. So if gamma is 2, that means that false positives are 4 times more damaging than false negatives. If gamma is a half, that's 1 over square root of 2, which is 1 over 1.414, which is pretty close to 2/3. 1.5 would be 3 halves, so the inverse of that is 2/3. So, roughly speaking, 2/3. That would roughly imply that false positives are 2/3 as important, or 2/3 as damaging as false negatives. So in other words, no matter how much I believe that, as long as I believe that false positives are less damaging than false negatives, I'm really willing to accept that this drug causes cancer. No problem. But even a modest increase in if I believe that false positives are more damaging than false negatives, even a modest increase in that belief causes these results to go from large-ish to nothing, to 0. So the argument that we make in the paper that supports this thinking, and incidentally this comes from a paper I wrote with Nathan Danneman, if you think that this is true, then the point of our paper is to say, let's not make decisions per se, let's just see how different people would make different decisions and see whether our overall conclusion is robust to a lot of different preferences that researchers might have. It's a way of trying to wiggle our way out of the problem that was posed at the beginning of this lecture, which is to say that statisticians are somewhat reluctant to impose their preferences on others and make decisions. Rather than do that, one might instead just say, well, specify a utility function that has a lot of flexibility in it and see if it's the case that people with a whole bunch of different preferences would make the same decision. And if they would, your result's really robust. And if not, your result's not as robust. In this example, the decision to conclude that a drug causes cancer is a very robust one. The decision to conclude that non-democracies are more susceptible to civil war is not very robust. So it turns decision theory into a robustness check on inference rather than a strict guide to inference. Well, that's it for this week. I hope you enjoyed this lecture, and I'll see you next time.